In this section, we're going to be covering the inverse Laplace and its application to solving differential equations. I'll preface this very quickly. In this section, doing the Laplace transformation to solve second order differential equations doesn't feel any better. In fact, it's probably worse than using the auxiliary equation, especially when it's homogeneous. But this technique isn't designed for these types of problems. They're more designed for complicated ones when you start to deal with the step function, the impulse function, and more complicated input functions. You know, that g of x at the very end after the equal sign. Or there's a special type of function these are really good with, which is integral defined functions. That's where like the function actually has an integral symbol in it. So as we're doing examples, it's going to feel like, wow, this is so much work. Why don't I just do like r squared and get the same answer? And to be honest, you're right. You should just do that. But this technique really shines with more complicated problems. But to really understand it, we're going to look at it in terms of simpler problems. So just keep that in mind as we go through this section. But before we can actually get into solving differential equations, we have to define the opposite operation of the Laplace, which is the inverse Laplace, right? So the Laplace transformation is invertible, meaning you can go backwards. And we define it as follow, as so f of s was the Laplace transformation. So if we're going backwards, we're going back to the t domain, and we're going to take the inverse Laplace, like that, of whatever the s function is. I'll make mistakes by putting the wrong variables from time to time, so I'll just be vigilant about it. But lowercase tends to be like going back to the t domain, and uppercase typically is the s domain. It's not an absolute notation, but it's more common when you see examples. So we're just going to go straight into covering some examples, and all it comes down to is just looking at the table and figuring out which one does it match in terms of, ones that I've seen before. So if I want to take the inverse Laplace of 1 over s, not 1 over s, let's do like 8 over s. So from there, you would just look at the table. So that's step one, look at table. And you notice that um, 1 is 1 over s, right? Like that's the transformation that we're used to seeing. So all we're doing now is just going backwards, right? So now we're just going backwards. So that's the inverse, and that's the Laplace. So that's all you have to think about in terms of that way. So then step two is to manipulate, right? So your goal is to make it look exactly how you see it on the table. And so we can still use those properties of linear transformations, which is we can break them up by plus or minus and we can factor out numbers. So the inverse Laplace of 8 over s is equal to 8 inverse Laplace of 1 over s. And then that's going to be equal to 8 times 1, which is equal to 8, right? This is from the table. And so f of t is equal to 8. And that's all it is. What makes these challenging is some of them require just algebraic manipulations that are kind of annoying, like completing the square or using something called the one trick, is what I call it, right? So it's just using a nice property about the number one, and we'll get to that. So let's just do another example. We're going to want to cover all of the main ones you're going to see, which is like the exponential, the polynomial, sine, cosine, and then the completing the square one, at least for now. So then we're going to take the inverse Laplace of 4 over s plus 3. That is an s, it's not a 5. Apologies if it looks like a 5. So step one is we're going to look at a table. And just so that we can have a handy table with us as we go through this process, we're just going to copy one in here. And so let's put it right above everything. So that's going to be the table that we're looking at. And this is the table that we do provide for you in the online exam if you're taking the online version of this class. So you are given this table. If you're taking an in-person class, you'd just be given this table at the end of the exam or something like that. So you don't have to memorize these ones. So if we look at the one that we have, we want S in the denominator. So it's all about where is S located. So we have S plus a number. So we look at our table and we see S minus a number. So that's a good candidate. The rest of them have S squared. That doesn't look like it. You just kind of go through each one and you figure out which one matches. So the only one that really works for us is the second one, right? So that's the one that we're thinking is going to be the right one. So we say E to the AT, or whatever letter you like to use, gives you 1 over S minus A, right? And then we're just going backwards now. So step 2 is to manipulate. So we're going to manipulate this and make it match what we see on the table. So taking our inverse Laplace, 4 over S plus 3. First thing I'm going to do is I'm going to factor out the 4. And I get 1 over S plus 3. And we notice that the formula originally has a minus sign. So using a little algebra trick, which just says a positive, addition can be written as a minus minus. So 1 over S minus negative 3, like that, because, minus minus equals a positive, using that nice little property. So then we can now say 4 Laplace transformation, sorry, 4, and then using the table is going to be 1 over, nope, this is where I mess up. I have to convert it to e. So e to the negative 3t. And again, make sure you're changing it uh, to the f of t variable, not s anymore. It's a very common mistake people make, and I still make it myself. It's just going back and forth between letters is sometimes a little challenging. So that's how you deal with the exponential case. So we got our one case where it's just 1 over s. This is the exponential. Now we're going to want to investigate, okay, so we deal with a lot of exponentials, we deal with a lot of polynomials. We're eventually going to have to deal with sine and cosine probably at some point. So let's do that one next, which is the sine and cosine one. Well, actually, yeah, we can do sine and cosine, and then we'll just do the polynomial. So example, let's do sine and cosine. So the inverse Laplace of 7s plus 4 over s squared plus, let's do, trying to think here, 36 maybe? Does that make sense? Yeah, we could do 36. It'll just give us a nice number in the denominator. Okay, so step 1 is we're going to look at the table. So this one's kind of interesting because here's the thing. Whenever you run into sine and cosine, they're almost always together. So whenever you see s squared in the denominator, immediately you're probably thinking sine and cosine. I mean, if you look at it, these all have s squared, and they're all related to sine, cosine. Sine h and cosine h are hyperbolic sine and hyperbolic cosine. We'll mention that later, just kind of defining what it is. Even the e to the at sine and e to the at cosine, they have a squared component, right? So typically, when you see sine squared, you're thinking sine and cosine. Um, so we're going to write down both of them because notice the numerator for sine has a number and the numerator for cosine has a letter s. If I look at my denominator, I have two terms, which means eventually I'm going to break it up. So our table says the following. So I'm going to write it this way now just to kind of get used to it. A over s squared plus a squared is equal to sine of at. And then the inverse Laplace of s over s squared plus a squared is equal to cosine of at. You will have the same denominator for both of them, which means you will have cosine and sine have the same number inside of the parentheses, assuming they come from the same fraction, right? So that's going to be our first step. The next thing we need to do now is to manipulate. So step 2 is going to be to manipulate. And I'm going to remind you of a quick trick, or not even a trick, a property of fractions, which says that if you add two numbers on the numerator of a fraction, you can break it up into individual terms like this. This is allowed. What you are not allowed to do, and I've seen many people do this, A over B plus C does not equal A over B plus A over C. It would be amazing if that were true, because then we would never need partial fraction decomposition. But unfortunately, that does not work. So we have to keep that in mind. Uh, so we're going to use that property. And so the inverse Laplace of 7s plus 4 over s squared plus 36 is equal to the inverse Laplace of 7s plus s squared plus 36 plus the inverse Laplace of 4 over s squared plus 36. So all I've done so far is just break it up into two different Laplace transformations, or inverse Laplace. And then now my goal is to make it look exactly the way I see it in the table. So the next thing I'm going to do is I am going to factor out any numbers that they have. And I'm just going to give myself a smidge more space like that. And so inverse Laplace, I can't factor out the s. So one thing to know about mathematics is whenever you have an operator, like a Laplace, a derivative, you're not allowed to factor out the variable that you're dealing with. So in this case, s is the main variable that's being worked on, so it can't be factored out of the Laplace transformation or inverse. Just like you can't factor out x if you're taking a derivative with respect to x out of the operator. Just you're not allowed to do that. And then here, I'm going to factor out a 4, and I get 1 over s squared plus 36. So I look at this and I recognize that, hey, I have s by itself, so cosine's almost done, but I need to write it in terms of this a squared. Now, eventually you can just look at it and be like, oh, I know what a squared is. It's just this number. So, but for this example, we're going to practice doing that. And we notice that, a squared is equal to a times a. So that means 36 is equal to 6 times 6. So s over s squared plus 6 squared. You don't have to write this, but in the beginning it doesn't hurt because it allows you to see, okay, that's the number that I'm going to be working with. So the only thing that's missing from this entire process is I notice that the cosine part's dealt with, right? It has everything I need. The sine part doesn't have a in the numerator, it doesn't have a 6. So this is where we're going to use a trick, which I call the one trick. And all it is 1 is a very special number in mathematics. It has this property where if you multiply, 5 times 1, that's equal to 5. Nothing happens to it, right? There is no change. And when you're doing algebraic manipulations, one of your goals is not to change anything usually. You want to maintain this equality, like everything's still the same. So we can use this property of multiplying by quote unquote 1 and manipulate it to make it look exactly the way we want to. So how do we do that? Well, we're going to use another property of fractions, which says the following. A number divided by a number that are the same, so same over same is equal to 1. So what do I mean? 5 divided by 5 is 1. So if I multiply this, and we know that 5 times 1 is 5, right? So what I could do here is I could say 7 inverse Laplace of s over s squared plus 6 squared. Notice that at no point are any of these 5s. They're all s's. So I try to avoid a 5 here. And what I'm going to do inside of the Laplace is I'm going to do this fancy trick of multiplying it by the number that I want in the numerator, which is 6. But I'm also going to divide it by 6 because 6 divided by 6 is 1, and 1 times anything is no change, right? So I have accomplished in the manipulation, but without changing it into something that's not what it's not supposed to be, right? So then from there, I do the final step. You don't even have to, but I recommend you do it in the beginning, is you factor out the denominator number. So 4 over 6. And then you leave the numerator 1 because that's what you want it to look like. And so now you recognize what A is, and you can now do the manipulation, right? So we have 6, 6, and 6 right here. So then this is equal to 7 cosine of 6t plus 2/3 sine of 6 times t. And now we have our Laplace transformation, inverse Laplace transformation, I should say, completed. And that's the entire process. All right, so now let's do an example with polynomial. So the polynomial is going to use the same trick, but they're also going to use factorials with it. So that's why it's a little bit more annoying. And if you've taken Calc 2, there's this one weird polynomial trick you learn in Calc 2 using the ratio test, which is you basically take like n plus 1 factorial and then you like break it down into like that number times n factorial. Thankfully, you don't have to do that here really, but you will have to deal with factorials within this problem. So just be very careful with carrying them around. So let's take the Laplace inverse of 7 over s cubed, like that. So we need to basically look at our table. That's the first step is table. And we notice that it's s to some degree, right? So if we go back to our table, there's a few of them, but chances are it's going to be e to the at, sorry, no, not e to the at, t to the n. The gamma function, you would see the gamma function in there, right? And the t to the n, e to the at, the number 11, you'll have like s minus a, right? I mean, you theoretically could do it with this one, and you would just get 0 for e to the at. So chances are it's going to be number 3, but theoretically it could be any of those. So we say the inverse Laplace of n factorial over s to the n plus 1. Let me just make sure I got that correctly. Yep, is equal to t to the nth degree, right? And then n is in even power. Sorry, not even power. It's in positive power. Yeah, positive integer. So, do you have to worry about S being positive or negative and all that stuff? Not really. Like, we'll always give it to you in a condition where you don't have to ever think about that. But theoretically, it could become an issue depending on your domain and stuff like that. Okay, so we have our table. Step 2. So we're going to have to identify n. That's the first thing. Is okay, identify n. So s cubed is really equal to s squared plus 1. So that means n is equal to 2. So basically, if you're doing s to the third power, t is going to be 1 degree less, right? Because you're going backwards. Okay, so we got that. Step 3 is we are going to create basically the factorial and manipulate so that we get it in the numerator. So what do I mean by that? It's going to be, say, manipulate to table form. So the inverse Laplace of 7 over s cubed is equal to, so I'm going to factor out the 7, and I get 1 over s cubed. Okay? And then from there, we are going to rewrite it as 7, and then we're going to do 1 over s2 plus 1, because that's just identifying what n is supposed to be. And so I need n to be 2 factorial. So using our one trick, right, we're going to do 1 over s 2 plus 1 times 2 factorial over 2 factorial, like that. And all we have to do now is just factor out the denominator, just because we don't need it there. And so we get 7 over 2 factorial, inverse Laplace of 2 factorial over s to the 2 plus 1. It matches exactly how I see it on the table. So then 2 factorial is just 2 times 1, so that's times 2. T squared. And that's f of t right there. So we were able to convert a, 1 over s to the n plus 1, or sorry, n factorial over s to the n plus 1 into a polynomial term. Or I guess technically it's a power because there's only one of them, but you would do it for multiple of them and you would get a polynomial. So in this next one, we are going to look at a case that you will come across from time to time with dealing with this, and that's going to be a problem that requires you to complete the square, right? So that's the purpose of this example, is to how do I complete the square? Because chances are most students have maybe heard of it, but probably don't know how to do it, or it was so long ago that they forgot how to do it. Me personally, I always forget how to do it until I have to reuse it for something, and then I remember it. So it's not something that's always on the top of my mind or something I could just do on command. But for the most part, I kind of remember the whole process. So step one is to look at table. So this is where it gets interesting because just looking at it, and if you look at our table, you don't really see anything that captures it, right? But you can think to yourself, well, I can kind of eliminate the things that it's not going to be. So 1 through 4, definitely not that one because there's quadratic. 5, 6, 7, and 8, I have an S term. So because I have the 8s in this problem, if you go back, there is no way to get rid of that where I only have s and a by itself. So the reality is we've actually eliminated 5 through 8 because it just there's an s term, so it's not a nice way of getting rid of it, right? So that really only leaves 9 and 10 kind of. If I look at 11, nah, probably, maybe. I mean, it could be 11. That's an option, maybe. Definitely not 12 through 19 because those are just other stuff. So honestly, it's either 9, 10, or 11. Like that's kind of where I'm looking at right now. Um, so essentially what happens is if I complete the square and I do not get a b squared term, like it somehow just gets canceled out, then I'm 11. But if I do have this b squared term, whatever that is, then it has to be 9 or 10. That's kind of what's going on, right? So if you're wondering, like, how do I know what to use from the table? Process of elimination, just get rid of things that you don't, and then just kind of fact or zone in on things that could work. So I'm gonna copy down the sine and cosine one, and then we'll have 11 in the back of our mind, but we probably don't need that one. So the inverse Laplace of, where'd it go? Sorry. B and S minus E. Okay. So B over S minus A squared plus B squared is equal to, and I'm just going to have this on my other screen so I don't have to keep going back and forth, uh, is equal to e to the at sine of bt, like that. And then the inverse Laplace of s minus a over s minus a squared plus b squared is equal to e to the at cosine of bt. Notice that sine is kind of nice in that it just needs a number, whereas cosine, they want more from you. They want a letter. So just something to think about. So we have an idea now. Looking at the form in the table, I have to make it look like that. And you probably wouldn't have intuitively thought, oh, I got to complete the square. But now you know, like this is me telling you, like if you ever have a polynomial in the denominator and you're taking the inverse Laplace, chances are it's complete the square. So that's where I would go next. So step two is to complete square. That's not how you spell square. Complete square of denominator. So how do we complete the square? So just for the sake of clarity, I am going to write this in terms of x because I don't want 5 and s to look similar. So we're going to do x squared minus 8x plus 20. Okay. There's several ways that people teach this, but I just kind of use the way that I learned and keep going with it. So what you do is you identify what b is, right? So let's identify what b is. So b is right here, the -8. You're going to take that number, okay? And you're going to divide it by 2. So 8 over -8 over 2 is equal to -4. Okay? So actually, it's not even, let's write it this way. Negative 4. From there, you're going to square it. Okay? So square it, which means you get 16. That is the complete the square process. Now you're going to use that information and you're going to create a manipulation. So what does this manipulation look like? Well, it looks like this. Essentially, you're going to rewrite it as x minus whatever you got from the division. So x minus 4. Actually, it's x plus negative 4. It's actually a plus and then 4 squared minus whatever you got from b over 2 squared, so that's 16. And then you're going to add 16 like that. Okay. Well, sorry. I'm confusing two parts to it. My apologies. It's going to be x squared minus 8x. I was like thinking of the second step in my head. Plus 20. And that 16 that you got, you're going to subtract it. Sorry, you're going to add it and subtract it. So you're going to do plus 16 minus 16. And just so that it's right next to it, we're actually going to write it like this. Okay. So this right here is the complete the square. Now, if you're wondering, why did we do that? Well, what happens is because of the method itself, the complete the square method, it's always going to factor in a very specific way. And the way that it factors is this. X plus b over 2 squared minus b squared over 2. Like that. That is always how it factors. Every single time. And of course, we still have the plus 20 out there, but the plus 20 isn't part of the form, right? So that means we're going to get x minus 4 squared minus 16 plus 20. That minus 16 is there because we needed it to compensate for the plus 16 I used for the manipulation. So if you didn't have that minus 16 there, you basically added a number that wasn't there to begin with, and you had no way of getting rid of it. So the minus 16 is basically a compensation to make sure that it's what we call the zero trick, right? I want you to think about that. What's 16 minus 16? It's zero. So theoretically, I haven't made any change to the equation, but this is a common thing we do in mathematics. We create zero out of nowhere through a very fancy way, which we call the zero trick, which is one of my least favorite tricks because a lot of the times it's not intuitive, and it just allows you to do manipulations that are very useful. Very common thing in calculus. So then we simplify to x minus 4 squared uh, plus 4. Okay. And now we have basically done the complete the square. So the Laplace inverse of 3s minus 17 over s squared minus 8s plus 20 has become the inverse Laplace of 3s minus 17 over s minus 4 squared plus 4, like that. One correction, the square should be outside the parentheses right there. So if you just saw it change right there, it's because I noticed the square is supposed to be on the outside. And that should be a 4. So now we have done the whole process. Now our job is to manipulate it to look like what we see on the table. So that's going to be the next step. So step 4 is going to be, or I guess this is step 3. Yeah, step 3 is to manipulate. So the inverse Laplace. So whenever you're dealing with sine and cosine, you have a S term and a non-S term. You're going to want to break it up into an S component and a constant component. Now, there are several ways that you can go about this, and I've seen it done differently. So I'm just going to do it the way that kind of feels comfortable for me. But again, it's a personal preference on how you want to do this. So we're going to do 3s minus 17 over. Uh, And so the problem with doing these types that a lot of students struggle with is you're not doing this problem in a vacuum, meaning like one step follows the next. You kind of also have to think ahead, right? We know that cosine is s minus a, right? Like we know that. So we want to manipulate this, and so we know a is equal to 4, and b squared is equal to 4, which implies that b is equal to 2, like by looking at it, which means the cosine needs an s minus 4 on the numerator. So I have to figure out a way to accomplish that. Okay? And so here's the tricky part. How do I do that? Well, you can kind of do it two ways. You can do fancy algebraic manipulation tricks. So, like, I'll show you this way, the way that they do it in the solution key. So, what they're going to do is this. They're going to say, you know that I want 4 in the numerator, right? So, what they're going to do is they're going to rewrite it as 12 minus 5. Sorry, incorrect. Plus 5. No, minus 5. Yeah, because 17. Now, I want you to look at why I would do that. It's because if I look closely, right, I put parentheses around this, I can rewrite this as 3 times s minus 4, because 4 times 3 is 12. And I get that. And so now I can break it up using our property of fractions. So all we're doing is breaking it up. There we go. And now we have s minus 4 in the numerator. So what am I missing here? Well, all I'm missing now is just a making it look exactly like the table. So I'm going to factor out a 3, and I get s minus 4 over s minus 4. And we know that 4 is 2 squared, just to emphasize that point. It is 2 squared. And then I'm going to factor out a negative 5, like that. And all I'm missing from this is I need in the numerator to be for sine. So let's go back to the original problem. Sine has to have b in the numerator. So we're going to do our little, one trick, which is to multiply the numerator and denominator by 2, because that's 1. So 1 over. The worst part about this is just having to rewrite this over and over again. That's never fun. So 2 times 2, sorry, 2 divided by 2 is 1, but then I factor out, oops, I got the 5. Factor out the 2 from the denominator. Again, at no point do I have a 5 except the negative 5 on the outside, so hopefully that's not too confusing. This is, in fact, a 5. Try to make it as obvious as possible. And then I have now a 2 in the denominator, which is b. And according to my table, it's going to be 3. E, and then A is 4. So if I go back, it's going to be A to the T. So it's going to be 4T cosine of 2T plus, nope, incorrect, minus 5 halves sine of 2T. I forgot the exponential part, didn't I? Now, if you're wondering, what kind of solution does this remind you of? Well, when we're doing damping problems have an exponential on each of these. So if I factored out e to the at and put it in front, this would be the damping problem. So re in reality, I just solved the damping problem. And you know what the cool thing about Laplace transformations and solving differential equations? It solves for your C1 and C2 in the process. So you don't ever have to do that step separately. The process of doing the Laplace transformation is incorporating the initial conditions. Now, whether or not this is easier is a personal question, but the trade-off is you don't have to do an extra step at the end, but clearly we have to do a lot of steps anyways, right? So that is our answer. That's f of t. So that's how we deal with completing the square. So just to illustrate completing the square for ax squared plus bx plus c equal to 0. We'll just put a 0 there. Um, it's going to factor. So step 1 is pick b. Step 2, b over 2. Step 3, b over 2 squared. Step 4, uh, oh yeah, sorry. There's one extra step. I forgot. I got to rewrite this. Step 1, uh, make a equal to 1. There cannot be a number in front of x squared. It has to be 1. So that's very important. And then divide b by 2. B over 2 squared. And then rewrite as ax squared plus bx plus c bx plus b over 2 squared minus b over 2 squared plus c, and then factor 2 x plus b over 2 squared minus b over 2 squared plus c. I'm not saying memorize that formula. I'm just saying that is the process in which I do it. Again, there's other ways people have taught this. So whatever you do and has helped you get to complete the square, go for it. You don't have to use this method if you have something that works better for you. Now we're going to shift our attention to taking the Laplace transformation and eventually inverse Laplace transformation of derivatives. So because we're dealing with differential equations, there are derivatives involved, so we have to be able to take the Laplace transformation of a derivative. And so I'm going to show you the entire process for just the first derivative. The second derivative is the same thing, just longer. And then the nth derivative is just much longer than we really have any time to want to go over. But a pattern emerges doing, first, second, third, and so on. So if you were to take the inverse Laplace, and you will never have to do this in actuality, but it's kind of a neat exercise. If you take the inverse Laplace of the first derivative of f, well, using the definition of the integral transform, what we end up getting is e to the negative st f prime of t dt. So we would use integration by parts to solve for this. So the integration by parts would be, okay, set u equal to negative st, and then set dv equal to f prime of t dt, like that. And then du would be equal to negative s e to the negative st dt. And then v would be equal to, well, the antiderivative of a derivative is just f of t, like that. So that's nice. I mean, came a lot nicer. And so if we actually, did integration by parts, we would get the limit as b approaches infinity of e to the negative st times f of t, so u times v, evaluated from 0 to b, minus the limit as b approaches infinity of the integral from 0 to b of negative s e to the negative st dt. Oops, I forgot f of t. So then we're going this way. And so notice that s is not the variable you're integrating with respect to. What that means is you can treat it like a constant. So what I could do, okay, is I can plug in infinity now. So e to the negative s times infinity, like that, of f of infinity minus e to the 0 f of 0, like that. And assuming that s is greater than 0, which is a fair assumption to make usually, what's going to happen is that this is going to go to 0 if s is greater than 0. Okay? And that's nice. E to the 0 right here, well, that just becomes a 1, right? We're used to e to the 0 becoming 1. And then on the other side, I'm going to factor out an s, make it positive, still not take the integral yet, like that. And so what this ends up simplifying to is minus f of 0, because e to the 1, sorry, e to the 0 is 1, plus s, limit, as b approaches infinity, of 0 to b e to the negative st f of t dt. And if you look very closely at that and you go back to the very beginning of this class, or sorry, chapter, that right there is just a definition of the Laplace transformation, e to the negative st f of t dt. So it turns out that we just have the definition, and so we end up getting this equation. And then just to make it look a little bit nicer, most people will write it this way. So that is the inverse, sorry, not the inverse, the regular Laplace transformation of f prime of t. It's just s times the Laplace transformation minus f of 0. So when we're doing these, there will be initial conditions that have to be considered because the process requires it. And also that's how you get your bounds and stuff like that. So that is the first derivative. Now, again, if I were to do the second derivative, it would just be the same thing, but just a little bit longer. We would actually use this result to show in the second derivative that we get that part as well. So extending to f double prime of t and f triple prime of t, we get the results. So just to kind of have them all together, we get s f of s minus f of 0. And then the Laplace transformation of f double prime of t is equal to s squared f of s minus s f of 0 minus f prime of 0. So notice that the s f of s minus f of 0 is kind of carried over in the next process, like it is slightly carried over. And then if we do the third derivative, I think the pattern really starts to emerge. S cubed f of s minus s f of 0, sorry, s squared, minus s f prime of 0 minus f double prime of 0. So as I'm going down, the s variable starts off at the level of whatever the derivative is, and then it's going down by 1. And then the function starts at the Laplace transformation f of s, and then it's going up in derivative starting with f, f prime, f double prime. But it only goes up to n minus 1 derivative. So notice that this is only the second derivative, not the third derivative, which is a common thing in differential equations. So generalizing this pattern. Now, good thing in this class, second order. We're not going to be doing three derivatives or nth derivatives, so you don't have to worry about that. They just take they take a lot more time, and the algebra is just so much more difficult to deal with that we wouldn't ask you to do that unless it was super easy, like the polynomial was like s cubed plus 8, right? Like that's just super easy. But again, they won't really do that, so. Laplace transformation, probably. I mean, I could always be wrong, but I've never really seen it. So remember, in parentheses, the n just means nth derivative is equal to Sn f of s minus Sn minus 1 f of 0 And these are all minuses too. Notice that. Sn minus 2 f prime of 0 minus, and then dot 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 minus s f prime, sorry, not prime, n minus 2 of 0 minus f n minus 1 derivative of 0. So the derivative gets bigger and bigger. And just a reminder, the Laplace transformation of f of t is equal to f of s. Just a constant reminder that that's true. Because we're going to be dealing um, with y a lot, unfortunately, my capital S's are just not very good, but that's basically what we're going to seeing a lot of in the examples we're going to be doing in the future. So a lot of capital Y of S's. So that's how you take the Laplace transformation of a derivative, and that is how we are going to solve initial value problems in second order with second order ones. So using Laplace transformation of the derivatives. Now, there is one aspect of it that's going to be very annoying, and that's going to be the whole idea of having to do partial fraction decomposition. So that part's never fun when dealing with the Laplace transformation and second order differential equations. So we're going to do a couple of examples of doing this, not mainly because of the partial fractions and like all the different cases of partial fractions that you kind of have to be familiar with. So if you don't feel comfortable with partial fraction decomposition, I do recommend reviewing it because it will be a big aspect of this. And sometimes in the homework or even potentially the exam, they will tell you the form of the partial fraction decomposition they're looking for just because that's kind of they have to tell you how to put the answer in the online exam. So just keep that in mind. But there is a level of similarity to what we covered when we did undetermined coefficients. So that process of finding A, B, C, and D will be very similar, but setting it up will be different. So there will be some similarity with what we have already seen before. So we're going to solve this differential equation. So solve the IVP, y double prime plus 7y prime minus 18y equals 0, given y of 0 equals 4 and y prime of 0 is equal to 3. Now, to be very clear, number one, you can't really use Laplace for boundary values because the Laplace transformation requires conditions for the derivative. So these are only really useful for IVPs. But theoretically, if I wanted to, I could just do r squared plus 7r minus 18 equals 0. Does that factor? Let's see, 2 times 9. So r minus 2, r plus 9. That makes sense. And that equals 0. So then my solution is y equals c1 e to the negative 2t plus c2 e to the 9t. And I'm going to tell you right now, uh, that's going to be the answer. Did I get the signs backward? I did. So there we go. And that took me, what, 30 seconds? So you're going to be like, why can't I just do that? And the answer is you can just do that. Like you're not being forced to do that unless the problem requires you to show steps in that you need to do the Laplace transformation. But at the end of the day, if I just ask you, solve an IVP, and I just want a final answer, you can use whatever technique you want. You're not limited to that unless you're told to do that. So just keep that in mind. You can always check your answer using the auxiliary equation. But for now, we just want to focus on how do I use the principles of the Laplace transformation to solve something like this? Because whenever you're verifying something works, it should be able to solve the easy things you already know how to solve before we can start jumping to the more difficult things like the step function and the delta function and stuff like that. So, step number one when doing this is just a formula. So, what's a very important formula that you're going to have to remember is that whole derivative thing. So, just I would do it for the second derivative. So that's going to be s squared y of s minus s y of 0 minus y prime of 0. Like that formula, if you don't remember, you can't do this, right? Um, and then y prime is going to be equal to, it's very similar to that one, s y of s minus y of 0. And then the Laplace transformation of y is a trick question. It's just y of s. It's a Laplace transformation, right? So don't overthink that one. I've seen people mess that one up before. So now we have our formulas. And what you're going to do now is just take the Laplace of both sides. So step two is Laplace both sides. So we're going to take the Laplace transformation. So, oh, and to be very clear, I never said this. The Laplace transformation of 0 is 0. Okay, so it's just 0. So we end up doing the Laplace transformation of y double prime plus 7y prime minus 18y equal the Laplace transformation of 0. Now, it's completely up to you how much work you want to show at this level. For this example, I'm going to show everything just so that we get comfortable using our properties. So I'm going to do the Laplace transformation of y double prime plus 7 Laplace transformation of y prime minus 18. And it's not a bad idea to do this because sometimes people forget to distribute numbers that they need to in terms of all of them. So that's the first step. We just took the Laplace of both sides. Step three is to evaluate and sub in initial conditions. So the Laplace transformation of y double prime is s squared y of s minus s y of 0 minus y prime of 0. So that's the first one. Plus 7. Okay, notice the 7's on the outside, so we're going to have to distribute that inside in a little bit. Sy of s minus y of 0 minus 18 y of s, and the Laplace transformation of 0 is 0. So from there, s squared minus y of s minus s, y of 0 is equal to 4 minus y prime of 0 is equal to 3 plus 7 sy of s minus 4 minus 18y of s equals 0. And we'll just do one more step of combining like terms. So then we get s squared. Whoops, there should not be a minus sign there. I don't know why I wrote that. Y of s minus 4s minus 3 plus 7s y of s minus 28 minus 18y of s equals 0. So all I'm doing is just combining everything. And then from here, I am going to essentially isolate y of s. Like that's my next goal. Okay. So that's step three. Step four is going to be isolate y of s. So if we take this line, then we're going to get s squared y of s. I'm going to start moving y of s terms together. So plus 7s y of s minus 18y of s minus 4s minus 28 minus 3 equals 0, right? And then what you're going to do is anything that does not have y of s, you're going to move it over to the right side, or the side that's not where y of s is, which is usually the right side. So I'm going to get 4s plus 31 right here, minus 31. And so when I moved it over, I added everything over, right? So we moved everything over and we get negative 30, sorry, positive 4s plus 31. Now notice that these all share a y of s term. which you're gonna have, you want that, like that's by design. Again, there's not a single 5 in this entire problem. So then we get y of s is factored out, and we get s squared plus 7s minus 18, like that. And there you go. We have isolated y of s. After we divide it over, we get 4s plus 31 over s squared plus 7s minus 18. And that sometimes is the answer on a homework problem or even exam problem, like find y of s, right? So we did all of this work, but I am still not near anywhere my answer because you got to remember, what am I trying to do here? I'm trying to find a function, y. Like that's my answer. Y of t equals solution. I don't have a t variable anywhere. It's an s variable. So in a way, I am making the problem a lot worse because I just went away from the variable that I wanted. But you have to remember, this is not a good example in general of the power of the Laplace transformation. It'll be later when we do more complicated functions, functions that we can't really do the auxiliary equation with. But what we have done is we have found a function in the S domain that when I take the inverse Laplace, right, just think about this. The inverse Laplace of y of s is what? Y of t. That's the solution. And I have y of s isolated, which means if I take the inverse Laplace of the left side, it has to be equal to whatever's on the right side, meaning the solution is just the right side's inverse, and I'm done. Like, that's the answer. So, in a way, my answer's right there. The only thing standing in the way is an inverse, which is never fun, honestly. So that's going to be the next step is taking the inverse Laplace transformation. But unfortunately, the more we look at this, we begin to realize that, yeah, we don't actually have a form of this that we have a table of. And you might be thinking, well, couldn't I just complete the square? I mean, you could complete the square and you could get an answer, but b is 7. 7 divided by 2 is a fraction, and then a fraction squared. Now you're dealing with a lot of fractions just to complete the square, and then you're going to have to manipulate your numbers to be fractions. I will tell you right now, doing that for most students would be way more challenging. Algebraically manipulating fractions to line up, it's just too difficult. So partial fraction decomposition is the better approach here because it doesn't really deal with fractions as much. It can still have fractions, but it's a more streamlined process in the entire aspect of it. So we're going to do partial fraction decomposition, or PFD. Now, you don't always have to do this. Sometimes the answer is very nice and you can just go straight into the table and get an answer, but this is not one of those, unfortunately. So we have to look at this and figure out, okay, which one is it going to be, right? So what does it mean to do partial fraction decomposition? Essentially, what you're doing is you're converting a fraction that you don't like with polynomial terms, or sorry, linear terms, product of linear terms, and you're just converting it into a nicer form. Essentially, what you're doing is this. You're converting this entire fraction into a over s plus a plus b over s plus b. Something like that. And you might be thinking, why would I want to do that? Sorry, I'll do minus because it doesn't matter. It's all the same. Well, I want you to think about it. If we go back to our table, right, go all the way back to our table, does our table have any forms for a number over s minus a? E to the at, right there. That's why we're doing it, because that's converting it into a form on the table. So partial fraction decomposition typically looks like something like this. Now, there are variations of it depending on how your form is going to look, but that's what we're aiming for, right? This is the goal. Okay, so that's our goal. So, in order to do your partial fraction decomposition, you're going to have to basically do some steps for it. So, what we're going to do here, okay, is we're going to create a side example. So, I'm going to write a bunch of new steps. So, side example. Find the partial fraction decomposition of, and I'm going to use the letter X here just because it's going to look nicer. That's literally the only reason. So this is a side example, and I'm just taking this one right here. So equal to 4x plus 31 over x squared plus 7x minus 18. Okay. And you usually learn this in Calc 2. I think in the Stewart textbook, it's 6.3 or 6.2. No, 6.3. 6.2 is trig substitution, which no one likes. I don't like it either, so it's very challenging. So to do our partial fraction decomposition, step number one is going to factor denominator, if possible. You can't always, and in the scenario that you cannot, you're not happy because you're going to have to do more work. But you need to always check to see if you can factor it. Okay. If it is factorable, it'll be very easily factorable. If it's not factorable, you'll immediately see that, oh yeah, I can't factor that. So uh, if you use the quadratic equation, so you can factor using the quadratic equation, believe it or not. Let's just say you do the quadratic equation and you get like x equals 2 or x equals 3. Like let's say you did the quadratic formula. All you have to do is move everything over to one side and then just multiply them. Like that's how you factor using the quadratic formula. You find the solutions, you move them over to one side, and you just multiply them, and that's your answer. If you ever get a fractional number, again, these are just little tricks if you want to use them. Let's say you get a fractional number. Multiply the numerator, sorry, the denominator over. So 2x equals 1, and then 2x minus 1 equals 0, so that it doesn't have a fraction in it. So 3x equals 2, and then 3x minus 2 equals 0, right? Like that looks nicer. You could do x minus a half. It's just most people don't like working with fractions. So just food for thought. If you don't like factoring and you still want to use the quadratic formula, you can factor by quadratic formula. But in this example, we'll just factor normally. So what multiplies to 18 negative and adds up to positive 7? So 1 times 18. Nope. 2 times 9. That's close. Yeah, 2 minus 9 could be like negative 7. So then we're going to get x, and we're going to get a 2 and a 9. But I want it to be negative 18, but positive 7. So this has to be the negative, and that has to be the positive because 9 minus 2 is positive 7. Right? Again, factor however it makes sense to you. So we have factor the denominator. So like that. Step two is to set up partial fraction decomposition, PFD, not PDF, but PFD. So this is how we set it up. And this is just something you're going to have to know in terms of like what kind of terms you have. And I will put up a table for you at the end of the, I can put it up right now. I just got to find the table for it, which I just get from like Paul's online notes. So this is the table that I would remember when you're dealing with partial fraction decomposition. And we'll just throw it in right here. So if your factor in the denominator is ax plus b, then your partial fraction term is going to be a over ax plus b. And then we'll deal one with later with the degrees. So you basically increase degree. And then ax squared plus bx plus c is when you cannot factor it, you get ax plus b. When you can't factor, it's because you have a complex solution. So that's when you get sine and cosine. You'll never deal with the bottom, the fourth one. If you ever get the fourth one, I would just stop that problem and move on. It's just gonna take you like an hour to do probably. That's a joke, but I'm telling you right now, if this was an exam and I had that question, I would just focus on everything else and do that one last because that would take a while. So let's see. We're going to get A over. Does it matter what order I put the terms in? Nope. Does not matter. Sometimes they'll tell you, like, hey, put the smaller number first, but that'll be in the directions. You don't have to. If you're doing it yourself, you don't care, right? So x minus 2 and x plus 9. So we have set up our partial fraction decomposition. Now, we don't want denominators. We want to get rid of all of the denominators. So the trick to doing that is multiply every single denominator everywhere, right? So step 3 is to multiply left denominator to both sides. So we're going to multiply left denominator to both sides. So what does that look like? I'm only going to do this once just because it takes up a ton of space when you show it over and over again. So x minus 2, x plus 9. And so we get x minus 2, x plus 9 is equal to a x minus 2, x plus 9. Like I said, I'm not even probably gonna have enough space here. Hopefully I can move it over. And if you do this correctly, you should always have where all the denominators cancel out. If they don't, you forgot something because they kind of have to, just by the design of this technique. These are all nines. I know they kind of look like A's. I apologize. The pen is very, it's a little thick for the PowerPoint, so it kind of looks like an A sometimes, like that. And if you do this correctly, you have a lot of cancellation. Cancel, 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 cancel. And what you end up getting is this. So there are several techniques that you kind of learn doing this. The main technique people learn doing this is so one of the textbooks I read, they call it the cover-up method, which kind of makes sense because you're just covering up a number essentially. When I took grad school, I actually learned this the more formal way, which was through limits. So what you're told usually is like pick a number that gets rid of a letter. So in this case, what number would get rid of a letter? Like 2, because 2 minus 2 is 0, and that gets rid of b. But the reality is this. When you divided everything by x minus 2 and x plus 9, you have actually removed it from the domain. You told the reader, hey, by me dividing with this variable, I am no longer allowed to use it because it's undefined. It's going to cause division by 0. But no one really focuses on the formal aspect. They just say, I'll find the singular points. You might hear it that way. Find the singular points and plug them in. Technically, you're not supposed to plug them in. You're supposed to take a limit and then plug them in. But we're not going to be that formal in this class. But I'm just letting you know if you ever see this in like a future linear systems theories class or anything like that, it'll come up. You'll see it as limits, which is kind of cool. So step 4 is to find singular points. Again, singular points just means division by 0, points of discontinuity or not discontinuity. Yeah, it can be discontinuity. Just points of interest, really. And that's just going to be x equals 2 and x equals negative 9. It's just the numbers that get rid of a variable. You won't always have, a number for every single letter, but you take as many as you get because the more you can use, the less work you do later. Okay. And then step 5 is plug into equation to solve for A and B. Okay. So if I plug in x equals 2, well, I get 4 times 2 plus 31 equals A times 2 plus 9 plus B times 2 minus 2. Well, hey, that just goes away. It's 0. So what I end up getting is 39 equal to 11a. So then a is equal to 39 over 11, which is very nice, right? I got a nice solution there. Fractional, unfortunately, but at least it's a nice-ish number. Better than a radical, I would say. So that's the first one. Now I just got to do it for the next singular point. So uh, x equal to -9, which means, what was it, 4 or 2? 4. 4 times -9 plus 31 is equal to a times -9 plus 9 plus b times, what was it, s minus 2? Will there be patterns to how the numbers emerge? Kind of. Typically the fractions all have the same denominator before you simplify them. So what you end up getting is you're going to get 5, right? Because 36 and 5, so -5 actually, equal to, and then this becomes 0 because -9 plus 9 is 0. And then you get -11b, so then b is equal to 5 over 11. So f of x is equal to 39 over 11 divided by x minus 2. I want to make sure that's correct. And then plus 5 over 11 over x plus 9. I always tell students don't manipulate the fractions or anything, just leave them in the numerator. You'll have to factor them out anyways. Okay? So that's the whole process of partial fraction decomposition using a method called the cover-up method, right? Again, in the future, I'll teach you a different method that'll be very similar to the non-homogeneous undetermined coefficients, but we didn't have to here because we were able to solve all of them using that singularity method, right? All right, so that's our side example. So now going back, to problem, our goal is to make it look like that. So y of s is equal to 4s plus 31 over s minus 2, s plus 9 is equal to, right? So doing this whole process, we got 39 over 11 divided by s minus 2 plus 5 over 11 s plus 9. Now we can take the inverse Laplace. So step number 4 of the partial, sorry, step 5 of the partial fraction decomposition is a whole problem itself from like Calc 2. So in reality, that was step 5, and then there was like 6, 7, 8, 9, 9 more steps, and then now we're back to step 10 essentially. So it's somewhat of a time-consuming process, but again, the purpose of this is to show that the method works, but we're going to use this in much more complicated problems in the future. So we have that. And so, sorry, I'm just going back and forth. Step 5, so now step 6. Inverse Laplace both sides. So the inverse Laplace of y of s is your solution, y of t. Like that's exactly what we want it to be. And then we're going to take the inverse Laplace of each of these individually because of the property of the Laplace transformation being a linear transformation allows us to do that. Not only that, we can factor out the fraction. And that's why I tell people don't mess with the fraction because you're going to end up factoring it out most of the time anyways. And we get all of this. And then according to our table, s minus a, these all become exponentials. And so we get e to the 2t. Remember, minus means plus exponent. And then plus 5 over 11. And then plus 9 becomes e to the -9t. And like I said earlier, when we did the auxiliary equation, we got this. We didn't have C1 and C2, but we had 2t and -9t. The advantage of the Laplace, though, is it does do the coefficient for you. Now, whether that's worth the trade-off of doing partial fraction decomposition, it's kind of a personal question, but it did work, and we got the solution. So now we're going to deal with the repeated root case. So this is the distinct real roots, right? Like this is what you would expect doing distinct real roots. You would have a nice factorable polynomial, quadratic really, um, two roots. Okay, what if you factor the denominator and you get a repeated root? Does that change the process? Not for the Laplace. All it changes is the partial fraction. So the big changing factor in most of these problems is going to be the partial fraction decomposition method, or you just have to use different functions from the table, right? So here we go. Solve the differential equation, sorry, the IVP, to be more specific, y double prime plus 2y prime, oops, that's a 12, plus 36y equals 0, given y of 0 equals 1, and y prime of 0 is equal to 1, negative. So again, auxiliary equation, 2 minutes, I'm done. But we're going to do the Laplace transformation because we like it so much. So step number one is formula. So just got to remind ourselves of the Laplace transformation of the derivatives, kind of like how we did y double prime with r squared. Now it's s squared y of s minus s y of 0 minus y prime of 0. As always, you don't have to do this step if you can memorize it, but it does give you a goal. There's no s there. Like that. Step two, Laplace transform both sides. Laplace both sides. So Laplace of y double prime plus 12y prime plus 36y equals Laplace transformation of 0. And then step three is going to be evaluate and simplify or plug in. So we're going to plug in our initial conditions. So just going straight into it, it's going to be s squared y of s minus s y of 0 minus y prime of 0 plus 12 s y of s minus y of 0 plus 36 y of s equals 0, right? And if you're wondering, does it become more challenging when it's not equal to 0? The honest answer is not that much. Your partial fraction decomposition might get a little bit more annoying, but not really. It really actually, this is one of the cases where the non-homogeneous doesn't get that much worse. It's actually on par. It's about the same. So I wouldn't be too worried about the non-homogeneous because it ends up being the same process, really. So now we're just plugging in our initial conditions to be careful with our negative signs. I want to make sure that we are distributing them correctly. Like that. And then I will do one more step on this slide just to simplify it a smidge more. And then after this, we are going to isolate y of s. So that's going to be our next slide. And that's going to be step 4. Isolate y of s. So we're going to copy that over. There we go. So factoring out a y of s. Actually, let's group them up first. That makes more sense to do. So s squared y of s plus 12y of s plus 36y of s minus s, that's not a 5, plus 1 minus 12 equals 0. And then s squared y of s plus 12y of s plus 36y of s. And then we're going to move everything over to the other side. So plus 11, I'm just looking at this. Yep, plus 11 looks good. And then we factor out the y of s from all of this. Oops, I forgot an s right here, didn't I? Yes, I did. S, S, and S. Like that. And then y of s is equal to s plus 11 over s squared plus 12s plus 36. So, huge part done. Sometimes that might just be the answer. They might just tell you find the function y of s for the problem. So they might not make you do the whole thing for every single problem, right? So this is probably the first four steps is the critical steps of being able to do every single one of these problems because they might ask you for one of the exam questions potentially. Just do that because we don't need you to solve every single one of them. We need you to demonstrate can you do this part of the process correctly, right? All right. Step five is partial fraction decomposition. So first we are going to see if we can factor this, which it turns out that we can. So it factors out perfectly in terms of s plus 6 times s plus 6, which means we have two terms that are the same, which means we get s plus 11 over s plus 6 squared. Okay? So because we have a squared term, we are going to deal with a different type of partial fraction decomposition here. So if you're wondering, could I have completed the square and do this? You actually could have completed the square, and you would still get s plus 6 squared because the 36 and negative 36 would have actually canceled each other out. So it would have canceled out perfectly. So we're going to do the setup. So y of s is equal to, actually, if they're this way, s plus 11 over s plus 6 squared is equal to a over s plus 6 plus b over s plus 6 squared. Again, if you're wondering, how do I know that one? If you go to number two, ax plus b to the k is a over ax plus b plus b in this case, over ax plus b squared, right? Notice that the degree of the denominator is going up by one on each of them. And you just keep doing that. The highest I've ever seen it go is like three, but since we're dealing with second order polynomials, sorry, second order differential equations, they're going to be second order polynomials. So you'll never go beyond two. Okay. So you don't have to worry about doing more than two, honestly. So we got that. Now, here's the thing. The cover up method that I showed you earlier, it still works, but not for the entire thing. So s plus 11 over s plus 6 squared equals a over s plus 6 plus b over s plus 6 squared. So multiplying denominator over, you're going to get a s plus 6 squared. And I should have given myself more space here. Like that. Right? So I'm multiplying everything over, everything with s plus 6 squared. Cancel, cancel. This cancels, but this becomes a 1, and then this cancels out completely. And so I get s plus 11 equals a times s plus 6 plus b, right? So I got an equation. The singular points is s equal to -6. That's the number that would make the denominator 0. So it's going to be the term that cancels something out. And subbing in gives uh, -6 plus 11 equals a times -6 plus 6 plus b. Well, that just becomes 0. And so what I end up getting is 5 equals b. Well, look at that. I got b. But the question is, well, how do I get a? I don't have any more singular points. Well, here's the beautiful part about mathematics. How many unknowns do you have now? One. It's b. How many equations do I have to solve for b? One. One equation, one unknown. I can solve for that. So I can now just pick whatever variable I want for s, or sorry, whatever number I want for s. I just can't pick -6 because I've already used it. So picking any value for s, we can solve for b. Are you always able to do this? Yes. But a lot of the times you have more than one unknown, so then no, it doesn't work. But I can pick whatever number I want for s. So using, I like 0, so using s equals 0, I get 0 plus 11 equals a times 0 plus 6 plus b, right? Sorry, I meant to solve for a, not b. We already know what b is. So then 11 equals a, sorry, 6a plus 5. And then so we get 6 equals 6a. So then a is equal to 1. And then I got a. That's good. I subtracted over the 5, right? So -5, -5, and then divide it over the 6. So now I have my y of s function. Thus, y of s, which used to be this complicated looking fractional function, which was s plus 11 over s squared plus 12s plus 36, we have transformed that into a sum of not linear terms, but decomposition of, fractions that contain, these nice terms, which would be then a was 1, s plus 6 plus 5 over s plus 6 squared. And you might be thinking, okay, how does that help me? Well, now I have terms that I can use a table on, right? So then this is where the inverse Laplace comes into play. So that was step 5. Now we're in step 6, inverse Laplace. So the inverse Laplace of y of s is equal to the inverse Laplace of 1 over s plus 6 plus the inverse Laplace of 5. Oh, our first 5. I apologize. Gonna get away from it. So the 5 on the numerator, s in the denominator. So this is y of t. So that's our final answer. 1 over s plus 6. According to our table, somewhere up here, that's e to the at, so that's just an exponential. That's just going to be e to the -6t. Okay. Now, knowing, from experience, I know that the second term is going to have e to the -6t because this is a repeated root. But we want to match it on the table. So if I go back to the table, s plus 6 squared, we look and we look, and we notice right here, number 11, we finally get to use it. S minus a to the n plus 1 on the denominator, n factorial on the denominator, and that's going to be t to the n e to the at. So this is where we're going to use number 11. So plus, we're going to factor out a 5, and we want 1 over s plus 6 squared, like that. And then using our little trick, so 1 plus 1, and what do we want? 1 factorial? That makes sense. So 1 factorial over 1 factorial. But here's the thing. 1 factorial is 1. So the reality is I don't even need to do that. So we're actually good because I have a 1 in the numerator. All right, this is 1 factorial. Just write stuff to the side. 1 is equal to 1 factorial. So then we get y of t is equal to e to the negative 6t plus 5t e to the negative 6t, according to the table, which says, I wish I could just have the table floating right next to us, but I can't. So s minus a, n plus 1, so n was 1, 1 factorial, 1, and then it becomes t to the 1 power e to the negative 6t because we have positive 6 on the inside. And there we go. That is how we deal with repeated roots and the Laplace transformation. So now let's do a problem where we have to deal with the polynomial, sorry, the quadratic not being factorable, and with sine and cosine, just to throw that in there, and the non-homogeneous case, right? So it's kind of throwing all things at once, but you'll realize that the non-homogeneous part, again, doesn't add too much more to it. It just makes the right side not zero. So you'll have a little bit more on the right side, but all it does is maybe make the partial fraction decomposition a little bit more annoying. So this one, if you can do this one, you can kind of do all of them because this kind of covers everything. So solve the IVP y double prime plus 16y equals cosine of 2t. Nope, wrong number, 7t. Given y of 0 equals 0 and y prime of 0 equals 0. Whenever it's trig, we love saying zeros because it makes our life easier. Okay, step 1, formula. Notice I don't have a first derivative. That's very important, so I don't even need to write the first derivative one because we don't need to use it here. And then, wait a second, n. Laplace transformation of y is equal to y of s. Step 2, Laplace both sides. So now there's no 0 on the right side, so now it makes it a little bit more interesting. If there was a y prime term, I can tell you right now, you would have to complete the square. Like it would be a complete the square problem because this is the purely imaginary case where the solution just has sine and cosine. There's no e to the x. But if there was a y prime, then there would be an e to the x component, which means there would be a complete the square. So that's the good thing is made it a lot easier by not including that y prime. So we Laplace both sides. And then step 3, actually, I could just break it up into the thing. Again, up to you how much you want to show for each of the beginning steps. It's just to get the brain going. And then step 3 is to evaluate and plug in initial conditions. So sy of s minus sy of 0 minus y prime of 0. So I got a square there. Plus 16y of s, and the Laplace transformation of cosine of 7t, 7 times t, you just got to be able to take a Laplace transformation. So cosine has s on the numerator, remember that. And then it's just s squared plus whatever the number inside the parentheses is, so 49. You could write 7 squared, doesn't matter. I would just write as 49. But yeah, there you go. And then now you just plug in your numbers. So s squared y of s minus s times 0 minus 0 plus 16y of s equal to s over s squared plus 49. And then makes this really easy. Y of s plus 16y of s equal to s over s squared plus 49. As of right now, there are no fives yet, so no fives. So we have done all that work, and we have shown that y of s is actually pretty nicely factorable, so we don't have to do any more work than that. So step 4 is to isolate y of s. Factor out the y of s, and then you're going to divide over the s squared plus 16. Remember, when you divide over stuff, it just goes into the denominator, usually. So s over s squared plus 16 times s squared plus, well, that should be 49. Let's put that one first. Doesn't matter, but just for the sake of consistency, like that. So we now have a y of s function, which just means if I can find the partial fraction decomposition, take the inverse Laplace, and you're good to go. Now, if you're wondering, you know, in the age of computers, at this point, you could just go into an inverse Laplace calculator, type in s over s squared plus 49 divided by s squared plus 16, you get the answer. Like you're done. So there are calculators online, Wolfram, AI, they can just give you the answer at this point. So just know that technology has gotten to the point where it is solvable. I mean, you could have just typed this differential equation into like Wolfram or some kind of AI and they'd give you the answer anyway. So um, it's not a bad idea every once in a while to like check to make sure you're at the point where it's correct, right? When you're learning, not when you're taking the exam, obviously. Step 5, partial fraction decomposition. Now, to be clear, you don't always have to do partial fraction decomposition. There are problems where you look at it and you realize, actually, I could just skip partial fraction decomposition and just get the answer. So don't always assume that you have to do it. It is sometimes, but not always, right? So we're going to rewrite this. So because they're both squared terms, so like s squared plus 49, s squared plus 16, unfortunately, we're going to have to do the annoying one. So it's going to look like this. Sorry, I don't know why that's right there. So again, these are not fives, they're s's. And it's going to be equal to a s plus b over s squared plus 49 plus cs plus d over s squared plus 16. Again, how did I get that? Look right here, ax squared plus bx plus c, ax plus b over ax squared plus bx plus c. B is 0, so there is no bx term, but that's where it comes from, right? So again, the last one, they will not give it to you on the exam. Again, if you ever saw that on an exam, just skip that problem and do it at the end. It'll take a long time. So now I need to multiply both sides by the denominators of the left side. So in doing so, we're going to get s is equal to as plus b over s squared plus 49. How do I want to do this? All right, you know what? It's because this problem is kind of annoying. I'll just do it all. So let's copy and paste it. And then give ourselves some space right here. In practice, you shouldn't have to write all this out, but for learning, why not? Put everything in parentheses. S squared plus 49, S squared plus 16, if I can fit that in there, kind of. Right? So multiply everything over by the left denominator. Cancel, 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 cancel. cancel that one, cancel that one, and we get S is equal to AS plus B. If you're doing scratch work, it's not a bad idea to write it in terms of X, but just make sure you change it back to S later. Just because a lot of students prefer to work with X versus say like S. CS plus D, S squared plus 49. Now, if you remember in the last examples, there was always a singular point that I could find to get rid of a letter. But here's the problem. There are no real numbers. There's only complex numbers, and we don't use complex number in this domain. This is a real domain problem. So S is limited to being real numbers, which means I can't do that. I can't plug in negative I or something like that. It just doesn't work for this process because at the end of the day, we only want real valued solutions. Um, so our technique doesn't work anymore for this type of problem, which means I'm going to have to use a different technique, which is basically grouping. So we're going to group all the squared terms together and every single variable. So in this case, we do get an S cubed. So you'll have to FOIL, unfortunately, right? Remember foiling. Uh, I'll just do this. Da, 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 da. AC plus AD plus BC plus BD, right? You're just doing that essentially. However you learn foiling. That's how I remember it. So we're gonna have to do that. So we're gonna do that on the next slide. Can move that over here just to make it look a little bit nicer. Oh, that was kind of weird. There we go. Okay, so foiling it out, we're gonna get AS squared. Nope, cubed. I'm already doing it wrong. Plus AS times 16, so 16 AS. Doesn't matter the order, just trying to make it look nice. Plus BS squared plus 16B. That's the first one. Plus CS cubed plus 49 CS plus DS squared plus 49 times D. Right? Just FOIL it all out. And then now I'm going to combine the S cubes with the S cubes, squares with squares, and so on and so on. So then we get AS cubed plus CS cubed plus BS squared plus DS squared plus 16AS plus 49CS. That's not an S, that was a 2. Once again, there are no 5s anywhere. Plus 16B plus 49D. And then just factor out. Right there and there. There and there. There and there. And we'll use every color at our disposal. And then these are just constants. Plus B plus D S squared plus 16A plus 49C S plus 16B plus 49 times D. Right? We have it all. And this is all equal to S. Like that's still all equal to S. Now, looks very familiar to undetermined coefficients. We just need to create a bunch of equations for each one, right? So setting up equations like undetermined coefficients for S cubed, S squared, S, and then constant, we have A plus C is equal to, well, on the left side, we have no cube term, right? There's no S cubed, 0, because there's no S cube term. For s squared, it's going to be b plus d equals 0. For s, it's going to be 1. 16a plus 49c equals 1. And then for the other one, it's 16b plus 49d equals 0, right? If you're wondering, could I set this up in a matrix on Desmos? The answer is yes, you could. You have to do a 4 by 4 though. A, B, C, D columns, and then it'd be 4 rows, 5 columns, one for the numbers at the end. But this is actually easy enough where you don't have to do that. So what you could do is just solve for one of the letters. A equals negative C. And then if you substitute it into, say, here, right? Then you could say, okay, we get 16 times negative c plus 49c equals 1, right? And then you get, what would that be? 49 minus 16 would be 33c equals 1, which means c is equal to 1 over 33. And then that implies that a is equal to negative 1 over 33, like that. And then if you do it right here, b is equal to negative d. Then this implies 16 times negative d plus 49d is equal to 0. I get 33d equal to 0. Oops. Which means d is equal to 0. And then that right here means b is equal to 0. So you could use linear algebra, or you can just plug it into the equations and kind of solve them individually. So y of s is now equal to, after this entire process, which was s squared plus 49 times s squared plus 16, has become, and I just got to make sure I put the coefficients in the right spot, as plus b. So a was negative 133, s plus 0 over s squared plus 49, plus c, 1 over 33s, plus 0 over s squared plus 16. One of the easiest mistakes a student can make, and this is just very frustrating to make as a, when you're doing a problem, is you get like the 49 and the 16 backwards. Like you just put them in the wrong spot. And so they just have the wrong coefficients, and like it's the worst mistake to ever make. So just pay attention to that. Especially if you're like looking at an example. That's another one. When you're like practicing these and you're looking at an example, it's very easy to copy a number from an example or maybe copy the order, and then it just messes up your problem. So just be very careful when you're doing that. So we now have solved the partial fraction decomposition. So we now go on to our next step, which is to take the inverse, right? Inverse Laplace. Also, notice they can technically kind of be combined, but you don't want to. Like you could combine these fractions into a single fraction, but when it comes to, well, if you think about it, with partial fraction decomposition, the goal is to take a fraction and uncombine them. So if you were to combine them for whatever reason, you'd just basically be undoing all your work, right? So that's kind of the whole point. So y of s, oops, sorry. The inverse Laplace of y of s, which again, I want you to remember, as you're doing this problem, what is your goal? My goal is to find y of t, the solution, and that comes from the inverse Laplace of y of s. If you always remember that, you won't get lost, because like doing this whole process, like sometimes I kind of forget what I'm even doing. But if I remember y of s is the bridge to the solution after the inverse, that's where I'm aiming for, right? So just remember that. Always keep sight of what your goal is in these problems. So then we get negative 1 over 33 s over s squared plus 49. plus the inverse Laplace of 1 over 33 s over s squared plus 16. And now you just kind of have to go back to what you know about Laplaces and just which one is it. So if we go to our table and we look, right, if I can find it quickly, according to our table, a number over s squared plus a squared is sine, but s over s squared plus a squared is cosine. So it's going to be cosine just because it's a number. Sorry, s over the whole thing. So I'm going to factor out the 1 over 33, and then 49 just becomes 7 squared plus 1 over 33, inverse Laplace, s over s squared plus 4 squared, except that's not a s, that's a 2. And then my solution is negative 1 over 33 cosine 7t, not 70, but 7 times t, plus 1 over 33 cosine 4 times t, like that. Just a side note, most of the examples we've been doing have very nice values for, s squared plus a squared plus b squared. But if you had s squared plus 7, you would just write this as s squared plus radical 7 squared, right? Like you could just rewrite a number as a radical. So just as a preface to that. So let's just write that as a side note. Side note. S squared plus, let's use the letter A, could be rewritten as s squared plus the square root of a squared. Just in case you ever run into that situation, which is very possible. So that's always, a possibility. Now, if you're wondering, would it ever be s squared minus a squared? The answer is no, because s squared minus a squared is called the difference of squares, which would be s minus a and s plus a. So that's the real root case. So you wouldn't have sine or cosine from that because you have real roots. Sine and cosine come from complex roots. So this would just be a regular partial fraction decomposition to these two linear terms or whatever they're called. So you never have to worry about the minus case because that's not cosine and sine essentially. So one more example, and this is kind of like, I'll call it the sanity check example, meaning you first might think, oh, I got to do partial fraction decomposition. But if you really think about it and just remind yourself, do I actually have to? The answer is no, right? So here's a piece of advice. If you're wondering, when do I know when to do partial fraction decomposition? 9 times out of 10, if there is an s in the numerator, you kind of have to do it with sine and cosine, right? Um, if there is no s in the numerator, then you can kind of investigate. That doesn't mean it's automatic, but usually when there's an s in the numerator or multiple terms, if there's more than one term in the numerator, 9 times out of 10, you kind of have to. But it really just depends on what the denominator is doing in the sense of like, well, what kind of roots do you have? Do you even have roots and stuff like that? So experience is key. But if you're never sure if you can factor it, chances are you probably have to do partial fraction decomposition. If you can't factor it, and it's not s squared plus a squared, then you might be able to do something else. And that's what this next example is going to show. So solve the IVP. Y double prime minus 2y prime plus 10y equal to 0, given y of 0 equals 0, and then y prime of 0 equals 3, right? So we're going to do our entire process of the Laplace transformation. And I'm not saying you couldn't do, what's it called, Laplace transformation. You could have. I mean, sorry, partial fraction decomposition. You easily can do it and just look at the correct answer. I'm just saying, this is one of the examples where if you try something else, you might skip that whole process. So step one, formula. Laplace transformation, y double prime is equal to
S squared y of s minus s y of 0 minus y prime of 0. Loss transformation of y prime is equal to s y of s minus s, no s, sorry, y of 0. And the Laplace transformation of y is y of s.
Step two, Laplace transformation.
So Laplace transformation of y double prime minus 2y prime plus 10y equals Laplace transformation of 0. And so we get this. Step three is to evaluate and sub in initial conditions. So we get s squared y of s minus s y of 0 minus y prime of 0 minus 2 s y of s minus y of 0. Let's see if I can fit this here. Plus 10y of s equals 0. And then if I plug in the numbers, I get s squared y of s minus 0 minus 3 minus 2 sy of s minus 0 plus 10y of s equals 0. So then we get s squared y of s minus 3 minus 2sy of s plus 10y of s equals 0. Step four, we're going to isolate y of s. So s squared y of s is equal to, sorry, not equal to, it's going to be subtracted by 2s y of s plus 10 y of s minus 3 equals 0. And then s squared y of s minus 2s y of s plus 10y of s equals 3. So I move the 3 over to the right side. And then we're just going to factor out the y of s. And just like that, we have factored out and isolated the y of s term. So it's at this point you would think, okay, I am going to do partial fraction decomposition because that's kind of the pattern that we've been doing for a while now. And so step five would be partial fraction decomposition, and y of s is equal to 3 over s squared minus 2s plus 10. And you try factoring it, 5 and 2, that work. Let's see. No, because 2 plus 5 is 3, so that doesn't work. 1 times 10, no. That's all I got, so not factorable. Which means, okay, then I gotta do this one, right? AS plus B over S squared minus 2S plus 10, which is one that we haven't done yet, but it's not impossible to do. It's just you're gonna have to do some work to calculate that. But here's the problem even beyond that. When you think about the end result, the denominator, I want you to think about the denominator. If you look back at the table, do you even have a formula that deals with quadratics? Like, if you look at all of these, none of these have quadratics in them in their quadratic form. They're all in this type of form. So notice here, s minus a squared plus b squared. Like, this is the closest I have to that, which means you have to remember, my end goal is I got to be able to use my table because I don't want to integrate. And in its current form, it's not anything I have on the table. So that means this is the wrong approach. Okay. You don't want to do this. So instead, complete the square. So not PFD, complete square. So we're going to complete the square here. So we're going to take 3. Sorry, we don't even need the 3. We're just going to do s squared minus 2s plus 10. I'm going to take -2. I'm going to divide it by 2, which is equal to -1. And then I'm going to take -1 and I'm going to square it, which is equal to +1. And so then s squared minus 2s plus 1 minus 1 plus 10. And then by the whole process, this is going to factor into something very specific, which is s uh, plus -1, so s minus 1 squared. Okay, that's just by design. And then it's going to be -1 plus 10. So then I get s minus 1 squared plus 9. Like that's my complete the square. And so we now have y of s is equal to 3 over s minus 1 squared plus 9, like that. And I have something in the table to deal with this. So step number 6 is inverse Laplace. So the inverse Laplace of y of s is going to be equal to the inverse Laplace of 3 over s minus 1 squared plus 9, which gives me 3 inverse Laplace of 1 over s minus 1 squared. Except now that I think about it, should I do that? Well, let me go back to the formula because I don't remember off the top of my head. What do I need to have in the numerator for this one? So it looks like I need to have whatever the b value is, right? So I instinctually always factor out the numerator, but we notice that if I write 3 squared right here, I should actually keep it in the numerator because now it matches up perfectly, right? And so according to my table, this is B and this is A, right? So this right here is B and this right here is A. And so this is y of t. So then y of t is equal to e to the t sine of 3t, like that. And there you go. That's all you had to do. There was no partial fraction decomposition. We just had to complete the square. And so my advice to you is, A, don't automatically assume you're doing partial fraction decomposition. Remember the big concept here. Your goal is to make it look like something on the table. We don't have a formula for a pure quadratic like we have with s squared minus 2s plus 10. Like there's no formula for that. So if you're running into a function that you can't factor, and it's not s squared plus a number squared, then it has to be complete the square, right? You kind of have to. Will there be problems where you do partial fraction decomposition on top of completing the square? Yes, there are problems like that. But those are just a little bit more challenging.